All right, let's get started so that the weekend can come earlier. Okay, so since we are still going over carbohydrate analysis, we'll just do a little bit of a recap before moving on. So how do we measure total carbohydrate? Where are my TAs for? I'll tell them. Okay, go ahead. What's that? Yes, absolutely. For nutritional labeling, it will be by difference. But if we have a simple matrix like you're going to do in the lab next Monday, what would be the test? Do you remember? Well, it is the phenol sulfuric acid method, where the sulfuric acid hydrolyzes the carbohydrate, the sugars, and make them a furan, different structures of furans, and then you react with phenol, and then you get a color, and you measure spectrophotometry, and you need a standard curve. And Chelsea, we have so far Drew and Vaidi for participation. Drew and Vaidi for participation, please. Participation points. Thank you. All right. What are the preparatory steps for carbohydrate analysis then? Yes, Sven?
You homogenize.
Yes, very good. So homogenization first. Second? Well, if you want to answer, go for it. You grind. So you homogenize. Well, homogenizing and grinding could be the same thing, but after that, if it is a high moisture, high fat, what do? We
remove the moisture and then extract the fat.
And we extract the fat. Okay, so let's say we did the homogenization. We selected a representative sample. Remember that you need to say that. You select a representative sample from a lot. You homogenize by grinding most of the time, and then you remove moisture and you remove fat. And then if we are interested in extraction of monodiene and oligosaccharide, how do we achieve that? Huh?
Enzymatic method.
Before the enzymatic methods, you want to extract them or separate them from proteins and starch. You need to do, if it's for enzymatic method, there is one procedure. If it's just chromatography method or colorimetric method, there is a special procedure that you would have to extract the monodiene oligosaccharide from the complex mixture, and that would be by solvent extraction. So basically you do 80% alcohol, ethanol extraction, and it is a hot ethanol extraction to extract monodiene oligosaccharides and polysaccharides and proteins with precipitate. There are purification steps we talked about last time, so you're responsible for knowing those as well. So what are some of the methods you can use to determine monodiene and oligosaccharides? Some of the methods, Vaidi already said enzymatic, so yes, you can do enzymatic. Another set of methods, we talked about it last time, yes? Colorimetric methods that are basically based on reducing power. Okay? You had your hand, yeah, what do you want to say, Ingrid?
Is it a certain chromatography?
Chromatographic method, which we'll cover today, Bill?
That's what I was going to say.
Bill was going to say chromatographic method, and that's what we'll transition into today. What is the basis? If you're using enzymatic method, how are you really measuring? What's the basis of this measurement? Remember the reactions that we talked about on Wednesday? No, I don't think anybody remembers. So basically you want to convert reactants to products and either have a reduction in absorbance or an increase in absorption as a particular wavelength. And then it's basically a spectrophotometric based method. So you will select specific enzymes for specific conversions where you can monitor changes in absorbance, either increase or decrease in absorbance. So that is the basis of carbohydrate methods. So as you've noticed, if you have noticed, some of the recap questions come back to you in a quiz or exam. So this is good that you can use these as study guides as well. They're not by any means encompassing everything, but definitely are important recap. So moving into chromatographic methods. So you have the qualitative methods, which are paper and thin layer chromatography, but these are not employed that often anymore. They're very kind of screening methods to see what types of saccharides you have, but it's not really the first method of choice for determining composition and quantification of your saccharides. But you've seen this gel or image before. It's paper chromatography or even thin layer chromatography, and you can see, you can visualize different components by autoradiography. And this is just FYI in terms of reminder of what the stationary phase could be made of and what would be a mobile phase. And if you're using thin layer chromatography, you have better resolution and separation of your peaks. Not peaks, dots in this case. So this is just FYI, a kind of a refresher to thin layer chromatography from the chromatography chapter. Okay, so by now you know all the different chromatography separation methods. So here we're going to specifically state how we apply them in carbohydrate analysis. So just a refresher, in normal phase HPLC, what would be your stationary phase and what would be the mobile phase? Who wants to state that? You should probably know that very well from your last exam. Stationary phase and mobile phase. Why am I seeing vague faces? Huh? Yeah.
For normal phase, the stationary phase is polar and the mobile phase is non-polar.
Okay, there was a common misunderstanding that is correct though, Agnes. There's a common misunderstanding that when you have stationary phase that is nonpolar, for instance, then your nonpolar compounds will repel the stationary phase. And I've seen at least 2 or 3 of you have this confusion. So it's unlike charges, like charges don't like each other and they repel each other. But when it comes to hydrophobicity and water loving and water disliking, it's not that case. So hydrophobic like to interact with hydrophobic because they are disliking water. Okay, so it's a different concept from a positive ion and a negative ion. They interact and the 2 positives do not interact. So it's, make sure you don't confuse these 2 different concepts. I noticed that in the exam, some of you confuse that concept. So when you have a stationary phase that is polar, then your polar components would like to interact with the stationary phase. And that's how they separate. If they don't interact with the stationary phase, they come in your void volume and they won't interact. So you want the interaction to occur. So reverse phase is the opposite. So what about anion exchange HPLC? What kind of ions we are separating? Oh, come on. Anion exchange chromatography. What are we separating, Ben? Anions. Thank you. So we are exchanging anions, negatively charged. So the stationary phase is what? The functional groups are positively charged. And the opposite is true for the cation exchange chromatography. I won't give up. I'm going to continue asking you. Okay. All right. So in the normal phase HPLC, the stationary phase that is most commonly used or can be used is unmodified silica. The cyanol groups, they can interact with the hydroxyl groups of carbohydrate by hydrogen bonding. So this is the type of interaction that occurs in this type of chromatography. However, since carbohydrate are very similar in terms of polarity, this can be very hard. You can get very the resolution won't be good, basically. You don't get good separation. So to enhance the separation using a polar phase, you add or you modify the silica to have amine groups on it. And when you add the amine groups, this becomes a hydrophilic interaction liquid chromatography, another kind of subset of normal phase liquid chromatography. So basically what you do is you react the silanol group with an amine group. So you end up having an NH2 group here, and the H will form hydrogen bonding with the OH groups on the carbohydrate. And that's how they would react. And the mobile phase will start off as nonpolar, and you increase polarity over time. So you start off with acetonitrile water, 50 to 85, or if it's an isocratic mode of separation, you select a concentration that will lead to resolution and elution of your peaks. To enhance separation and resolution, you would normally work with the column temperature, increase the temperature of the column so that you enhance separation. Okay, so the detection usually coupled with mono and disaccharides and oligosaccharides is usually refractive index detector. That's a very common detector used for carbohydrate analysis. However, gradient elution is not possible when you use RI. Why is that?
Because you're measuring in reference to your mobile phase, so if you change your mobile phase, your reference changes.
Yeah. So usually in your detection, you have your mobile phase passing through a detection, and that would be your base, and then your sample will go in and get detected, and you will detect a change in refractive index, and this is how quantification occurs. So if your mobile phase is changing, then you can't have an accurate detection of the quantification. It's generally insensitive, meaning you have to have a certain concentration. Below a certain concentration, you won't have a good detection or good distinguishing between two closely related concentrations. And it's not specific. It will detect carbohydrate, but it doesn't necessarily have a specific signal to different carbohydrates. And the order of elution, usually you start with monosaccharides to saccharide, disaccharides, and then oligosaccharides. Because it's based on hydrogen bonding interaction, the more you have, if you have a monosaccharide, you have a certain amount of OHs. If you have a disaccharide, you have more OHs, and oligosaccharide more OHs. So there are more groups for interaction forming hydrogen bonding with your column. So they will be retained longer on your column. But there is a problem with having an amine group and a sugar group. And that problem basically over time, the columns get degraded at a particular temperature that you would use to run your separation. You might end up having Maillard reaction actually. And this will result in depletion of the amine groups or blockage of your amine groups on the column. So to solve this problem, you have modifiers, meaning you add amine groups in your mobile phase, so you are continuously replenishing your amine group supply on the column. There are other groups that you can use to modify the silica that will also form hydrogen bonding with your sugars. Reverse phase chromatography, the way it's applied, and you will have a reverse phase C18 column, like the one we use in the lab for caffeine, and your mobile phase will be mostly water. So the problem is separation of different monosaccharide is really difficult. Why is that? Why is it hard to separate monosaccharides like glucose from fructose, for example, using reverse phase? Think about your chemistry background a little bit. Yes? They are very similar in polarity. They don't want to stay on the column a long time. So they want the elution time is really fast. And when you have fast elution time, you have poor resolution. So you want them to be retained somehow on the column. The way they do it, so what can be done is basically adding salt. You can add salt to your mobile phase, make your mobile phase less polar. So then your sugars will tend to retain a little bit longer on the column and not go out with your mobile phase. However, the reverse phase chromatography is affected by presence of anomers, meaning the alpha and the beta isomers. So in order, and then you'll have split peak. If you have those two present at the same time, you won't have a good one peak, you'll have split peak. To avoid that, sometimes you add amine groups to your mobile phase, and it causes the conversion of one form to the other, basically, and make sure you have one form that can be detected. So, believe it or not, you can use anion exchange to separate carbohydrates. Carbohydrates are not naturally charged groups, so you can make them charged by increasing the pH. If you increase the pH, then they will lose an H and become negatively charged. So they are very, very weak acids. They don't give you their hydrogen very easily unless you increase the pH. So if you want to use anion exchange chromatography to separate sugars, then you want to make sure that the pH is alkaline. So with anion exchange chromatography, then you have what you've seen before in the chromatography chapter. You have the polystyrene divinylbenzene polymers as your functional groups that will be derivatized here into anion exchangers. Since these sugars can be oxidized, then you can use the pulse amperometric detection, which is based on detection changes in current in products that will oxidize or be reduced. So it's an electrochemical detector. Again, you want to remember your detectors from the HPLC chapter. What do you think the order of elution is in this case? Which ones will tend to be more charged at high pH, carry more charge? Oligosaccharides, disaccharides, or monosaccharides? Think of how many OH groups would be available on a mono versus a di versus an oligo. Huh? I heard something. Did you say what? Oligosaccharides, you have more groups of OHs. So then they will carry more charge so they will have higher charge valence at higher pH.
So, oligosaccharides do first?
No, actually interact more with the column. Oh, did I confuse you in terms of order of elution? Sorry. Yeah, you were right. Monosaccharides will elute first, and then the what? Yeah, monosaccharides will elute first, and then the more OHs you have, the more charges you're gonna carry. What?
Does ratio of OHs to size matter?
The ratio of OH to size matter. I'm not certain. Why do you?
Never mind, just keep going.
Huh? Do you know anything that we want to
I'm
share?
just wondering. Yeah.
No, it would be mostly the location of the OH, whether it's an alpha, or is the location of the OH, the stereochemistry of the sugar itself, but not necessarily structure, whether it is fructose or glucose. Anyway, both fructose and glucose at high pH become aldehydes. So fructose is no longer a ketose under alkaline conditions. Okay, so cation exchange. So you can also use a cation exchange, but there's no way you can make the sugar positively charged. So no matter how you change the pH, the sugar will not carry a positive charge. In this case, you would use counter ions. So you will have your stationary phase that is negatively charged, and you'll add counter ions that are positively charged, such as calcium or silver. Or you can also use acid, diluted acid, so that you have proton. So what happens is your counter ion will react with your carbohydrate in the OH groups, and that once they interact via coordination complexes, we call them, this will interact with the negatively charged stationary phase, and that's how you get the separation. And usually cation exchange HPLCs are both a combination of an ion exchange and size exclusion. So since it's a combination of size exclusion and ion exchange, the largest will come first. So you'll have in this case sucrose, glucose, fructose order. So the largest in size, in geometric size, will in this case come out first. So your mobile phase will be mostly water and carrying the metals, the counter ions. Or it can be diluted acid as a source of proton. You can also do gas chromatography for carbohydrate analysis. But how can we make the carbohydrate detectable or detected by GC? Are carbohydrates volatile? No. You had your hand up, Drew. So carbohydrates are not volatile and they're not thermally stable, so they require derivatization, basically. So usually there are different types of derivatization. You have the silation or silylation derivatives are more volatile than acetylated, so you can do acetylation, you can do silylation, but depending on the application that you have. For example, silylation is for disaccharides, acetylation would be good enough for monosaccharides. So there is a first step where you reduce your sugar to sugar alcohol. Use sodium borohydride to do that. And then from there you do the acetylation, and then you end up with a product that is thermally stable and volatile, and that's how you measure it. And this is just a chromatogram showing that you can have internal standards, and then you have your sugars of interest as well that can be analyzed. Common detectors FID, and then fused silica, column HB5MS for a stationary phase. Questions on monodioligosaccharides? Yes, Sarah.
Why would you choose one method over the other?
Very good question. Why do we, actually we asked, we talked about it briefly when we covered the chromatography chapter. You have so many different modes of separation. Why would you choose one over the other? It depends on what's published and known. what you have available in your lab, what you're comfortable with using. And sometimes if you're having a hard time with normal phase or reverse phase chromatography, for example, you say, okay, I'm going to do anion exchange chromatography to ensure good separation. So yeah, you would just pick a method and try to make sure it works and it's validated and you go with it. There are always tons of methods you can choose from. Okay, so moving on to starch and dietary fiber, these are large carbohydrates. For starch, the method we're going to talk about today, total starch, degree of gelatinization, and degree of retrogradation. So there's a qualitative analysis of starch. Basically, if you want to detect the presence of starch, if you put iodine will interact with the starch physically, and then will give you a strong blue to purple color as an indication of presence of starch. And that is, starch is often actually used as an indicator in a reaction, where you have iodine as one of the reactants. You will probably see that in later chapters. But anyway, so because of the strong interactions of iodine and starch, it is a qualitative method that will confirm whether or not you have starch, and it can be used as means of identification and use starch as an indicator. Microscopy is a physical method for looking at starch, and you can identify different grains based on the structure of the starch granules. You use microscopy to look at those different starch granules, the swelling of starch, morphology basically of the starch. Quantitative of total starch is most commonly used is an enzymatic method. So in our enzymatic methods, so in using enzymes, starch is converted totally to glucose by enzymes. From your food chemistry, what enzymes can break up starch? Bill. Amylase. So amylase will break up starch into what kind of molecules? Which amylase will give you maltose? Without looking at your slides. Try to remember your food chemistry. Yeah? Actually beta amylase. So beta amylase will give you maltose. Alpha amylase is basically random. It's an endoenzyme that will break the carbohydrate or starch at different locations inside of that starch molecule. So alpha amylases, but you want to make sure you have glucose. Everything is converted to glucose. What enzyme do you need?
Amyloglucosidase?
Amyloglucosidase or glucoamylase. So here's this chart. I don't know if you've seen this chart in food chemistry, but the glucoamylase is an exoenzyme, so it breaks from the exterior one glycosidic bond at a time. So it takes one glucose and chop it off. Recognizes only one sugar and monosaccharide and breaks it off. So that's the name glucoamylase. So the alpha amylase, like I said, it's an endoenzyme, so it would cleave interior to the starch molecule and gives you, we call these molecules maltodextrins. So because they are maltodextrins, because they are basically several units of dextrins or dextroses. So several units of glucose, but not complete starch molecules, so they're maltodextrin. They vary in their degree of polymerization, basically. So if I want to get everything to glucose, I have to add, first of all, facilitate the breakage of the large starch molecule into smaller molecules, and then smaller chain that is, and then use the glucoamylase. So there are two different enzymes that are key that you want to use as well. You want the debranching enzyme, Polynase will break off the alpha-1,6 linkage, specific for alpha-1,6. Alpha amylase and beta amylase are actually specific to the alpha-1,4 linkage. So beta amylase is also important, and when we talk about retrogradation and gelatinization, beta amylase becomes an important enzyme because it cleaves 2 glucose units at a time, and that gives you maltose. And that is important later on for a different analysis. So it's good to understand the different enzymes because based on the enzyme used, we can quantify either starch, gelatinized starch, or retrograded starch. So we break off starch into glucose using this combination of enzymes, and then with glucose, you can use enzymatic reaction. This is not slightly, different set of enzyme reaction than the example I gave you last Wednesday. Here you use the enzyme glucose oxidase. So you will form a peroxide as a side product, and the peroxide will oxidize a dye, specific compound or molecule, and with the use of peroxidase for oxidation, and then you would generate an oxidized dye that is colored, and that would be your measuring reaction. You would determine the amount of oxidized dye generated by measuring absorbance, and you can calculate back the glucose amount to determine total starch. You need obviously a standard curve, and you would use glucose as a standard curve for standard curve. Degree of gelatinization and degree of retrogradation. If you remember at the beginning of the lecture on Wednesday, I asked you, can you use the same method for both? And one of you said yes, and here's why. So if you look at starch and the enzyme, I want to go back to this. Beta amylase and polynase do not act on raw starch. So if the starch is not cooked, or if the starch is retrograded, they cannot digest it. They cannot break these bonds. Okay? So they can hydrolyze gelatinized starch. They cannot hydrolyze retrograded starch. And that's why the same method can be used for both. So if you want to measure degree of gelatinization, then you would use a combination of polynase and alpha amylase, and then measure the reducing power of the resultant solution, where it will have maltose and maltotriose with the reducing end. And then you can measure the reducing sugar using one of the methods we talked about last time. That's Morgi-Nelson method, for example, with the arsenopyrrolate reagent. So you can do that. If you're suspecting retrogradation and you want to determine how much retrogradation occurred, then you would do the same thing, but instead you won't get as much maltoses and maltotriosis. You won't have as much reducing power. So there is a conversion to determine how much retrogradation occurred in a particular product. So the same method can be used for both, but the outcome is different. One, you will have high reducing power, telling you that the starch has been gelatinized. The other, low reducing, because after gelatinization you got retrogradation, and again the enzymes won't be able to function or digest retrograded starch. Any questions about the starch? All right, so the last bit in the carbohydrate analysis is the dietary fiber. So as you all know, dietary fiber is the edible component of food that is not digestible by our body. So the dietary fiber encompasses polysaccharides such as celluloses and hemicelluloses, oligosaccharides such as oligofructans. Can you give an example of oligofructan? A very common one. Do you know what inulin is? So inulin is a fructose polymer, but the end of it, one of the extremities is glucose. So it's a dietary fiber. And lignin, it's not a polysaccharide, it's not a carbohydrate, but it's a dietary fiber. So dietary fiber is divided into two components. You have the soluble fiber, that is pectin and hydrocolloids or gums. And these are some of the produces that are rich in soluble fiber. And you have the insoluble fiber that is mainly the cell wall material, such as cellulose, hemicellulose, lignin, and not necessarily cell wall material is the resistant starch. We talked about the 4 different types of resistant starch. Wheat bran and whole grains are high in insoluble fiber, or rich in insoluble fiber. So is it possible, since they are very diverse, is it possible to have one single approach to analyze dietary fiber? No, it's an extensive procedure and it's very involved because of solubility is key. If they are different in solubility, then we really need to be creative in the method to make sure that the method we follow actually quantify all of them. So you won't find this in your book anymore. The older edition of the book had it, and I still keep it in my slide because, I mean, it's good to know that you used to quantify something known as crude fiber, but now no more for foods. It's mostly used for animals. And the reason for that is the way you determine crude fiber, or the approximate amount of fiber, is you have a series of acid or alkaline extractions. And using acid or alkaline extraction, so you do acid first and then alkaline followed by alkaline, what happens is you're digesting starch, you're digesting the proteins, your fat is also being solubilized. Then what you end up with is your insoluble fiber will precipitate, will not be hydrolyzed. But you will lose the soluble fiber. So you're only measuring really here cellulose, hemicellulose, and lignin with that. You can't measure hydrocolloids or pectin. So it's an incomplete quantification of your fiber. The detergent extraction is also the same issue. You have the acid detergent extraction, you can only determine cellulose and lignin. If you have neutral detergent, you can only determine cellulose, lignin, and hemicellulose. But none of these methods will allow you to determine the soluble fiber. So that's why they're used, if they're used nowadays for animal feed, not necessarily, not for food. So your one and only method, or the most common method for dietary fiber, is based on enzymatic analysis. And Jenny's smiling, she spends days and days and days, right? Yeah. Okay. And she loves that method. Okay. So basically, you want to digest everything but your fiber. So you start with a sample that's been homogenized, pre-dried, fat-free, and then you do digestion. Sometimes you need to heat if you know that you have a starch that is raw starch. So you want to heat it a little bit to gelatinize it so that you can digest it with alpha amylase, and then digest it with glucoamylase, because you want to make sure that everything is soluble in the water, in the aqueous, and can be removed. And then you digest also with protease so that you can break down the proteins into amino acids and peptides so that also can be solubilized and removed. Caution that different enzymes might require different temperature and pH, so this could be adjusted and with the different types of enzyme you use. So there is a standard method, IACC standard method, right, or AOAC standard. There are different types of standard methods, but they're all based on the same principle, but it at least gives you the pH, time, and temperature for each step. So at this point, what you can do, you still have your pectin and hydrocolloids with the soluble component, right? So you have the insoluble fiber, it will be a precipitate, but if you want to determine total dietary fiber, at this point, you don't want to separate soluble versus insoluble. At this step, you add ethanol. Ethanol will precipitate pectin and hydrocolloids, and then you will have, you can have a separation, filtration. You wash several times with ethanol, and then you dry, and then you have your dietary fiber. You want to make sure you correct for protein and ash, because you might have with your fiber some remaining proteins and ash. So you want to correct for that, meaning you determine the amount of protein, you determine the amount of ash in that final residue that you have collected, and you subtract the weight of the protein and the weight of the ash, so that you only have the weight of the fiber. It's a very important step to correct for at the end, and then you get your total dietary fiber. Now, yeah? You get rid of the fat from the beginning. Okay. So, however, if you want to determine how much soluble dietary fiber you have versus insoluble dietary fiber, then this step will not be done here. So you won't add ethanol, you will just filter, and when you filter, you're going to get the residue and you're going to get your solubles. Okay, so your residue is your insoluble fiber. So after you hydrolyze with protein and enzyme, the amylase, glucoamylase, then you'll end up with a precipitate that is mainly made of insoluble fiber. You wash with water, ethanol, acetone, make sure everything is, if there's any residual of any organic solvent, soluble matter, it will be removed. You dry it and you weigh it. Again, you have to determine residual protein and ash and correct for those, subtract them from your dietary fiber. You got your insoluble fiber. For the soluble, if you remember the diagram, if I go back here, you have the residue and you have the soluble. So the residue, this is the path for the residue. This is the path for your filtrate, the soluble matter. In it, you have your amino acids that were broken off, you have your sugars, and you have your pectin and hydrocolloids. So you want to get your pectin and hydrocolloids and gums from here. So you precipitate with ethanol at this step. Here, when you precipitate with ethanol, your pectin, hydrocolloids, and gums are precipitated as soluble fiber, and then the solubles you discard. Then again, you have a series of washes to clean, make sure nothing else is in that residue, and the final residue you have to correct for protein and ash. Any questions here? Okay, this is one of my favorite methods, just saying. Maybe you need to study it well. Okay, total insoluble and soluble fiber, you can use GC, yes?
Earlier you said to skip step C.
No, I did, well, skip step C if you want to get soluble and insoluble amounts separated.
So what would you get if you, so if you just told, you would get total.
Total dietary fiber. If you go to step C and you go right to ethanol step, then you're precipitating pectin and hydrocolloid with the non-soluble fiber.
Okay, so
Then you'll get the total dietary fiber.
and then you filter and wash and be done.
You filter, wash, and be done.
Okay.
Next.
So just to confirm, like all these methods are to like analyze the type of carbohydrates after like we've done the protein, all that stuff.
Where?
Like just total carbohydrates. So like after we've done protein and fat and ash and everything like this, is this, and we get our total carbohydrates, this is just then to determine the types?
Yes. So the total carbohydrate that you get by subtraction is just a number that you put on your nutrition label. here, but under total carbohydrate, you have sugars, you have oligosaccharides, you have starch, you have dietary fiber. So yes, so what we're covering here is the different types of carbohydrate. You're right. Okay. So back to this, you can use GC, and in GC you can actually get the different monomers form of the different dietary fiber components you have. So again, the same preparatory step, you get rid of starch, you get rid of protein, and then you actually at this point you precipitate, you do step C, you precipitate with ethanol to get all the dietary fiber. And then from there, you use strong sulfuric acid to liberate monosaccharides. And you get your neutral sugars, and uronic acids are part of pectin, right? Galactouronic acid is a subunit of pectin. So you get the neutral sugars, you use GCFID. Like we said, you do a derivatization step, and then you can measure those individually, and you get their amounts individually. And then you get the amount of uronic acid by taking the same extract and running a calorimetric method. You determine the amount of uronic acid, you add it to the amount of monomers that you get, and then you will get the total carbohydrate, or total dietary fiber. The benefit of a GCFID is actually it will tell you the monomers that you have, and you can trace it back to, is it hemicellulose, cellulose? Well, you might not differentiate much between those, but you will differentiate whether how much pectin you have versus cellulose versus lignin. Because the lignin is, as I told you, their monomers are not glucosides. Yeah. Pectin analysis is often done for products such as jams and jellies, and it's based on the precipitation with alcohol. So basically you precipitate the pectin, separated from everything else that is typically soluble, and you subject it to saponification and acidification and precipitation. The reason we do saponification is because it's really hard to break the glycosidic linkages of uronic acid and the galactose. The galactouronic acid bonds are really hard to break. So the saponification step allows for the removal of this methyl group, and when you have acidification in the presence of calcium, you form bridges, and then you can precipitate and measure the gravimetric measurements, measure the weight of the precipitate. Okay, so this is something that I would like you to do for, let's say, next Wednesday. It's a +5. So you do that. This is a question. It just shows you or gives you an idea of how you will determine dietary fiber, the soluble and insoluble, from data that has been collected. You won't be determining dietary fiber in lab, so this is just an exercise to do a paper calculation exercise to determine insoluble and soluble. So give it a go and turn it in, and I will actually post the key on Moodle after you turn in the work. I need to make sure that you know how to determine, using data collected, the amount of dietary fiber. So this is just a hint to tell you how to go about answering this question, what measurements you need to do and get. For lab, on Monday, you're going to do the total phenolic sulfuric acid method for total carbohydrate. You're going to use your lab manual this time, not the addendum, so you'll find that chapter 6 in the lab manual. Please review chapter 10 in the textbook, and I will post, I think I did post it already, but I'll make sure that it's posted. And you need your laptops. You're going to do calculations in lab and be done with calculations in lab. I will send you the Excel sheet that you would need for lab next week. And on Monday, Just a reminder, you have the guest lecture, Dr. Nielsen. She is a treat. I hope you'll enjoy her.